Before we can discuss spring potential energy, we first have to discuss spring force. We didn't have to do this for gravitational potential energy because we'd already talked about the force due to gravity in the previous topic. So first I have to introduce spring force so that we can then use that to find the potential energy due to that force. So the spring force is calculated by K times X, where K is the spring constant. And this is a constant inherent to the spring itself. So a very stiff spring is going to have a large spring constant, and a very loose spring is going to have a small spring constant. And these can range anywhere from a couple of newtons per meter all the way up to tens to hundreds of thousands, depending upon something like a braking system that needs a really stiff spring in order to prevent a lot of wiggle once you try to stop. Whenever we deal with X, X is the distance from equilibrium the spring has been stretched or compressed. So in white here I have just a spring, it's been hooked up, attached to a wall, so it's a horizontal spring, and it's just allowed to sit there. That's its equilibrium position. Once you pull it back and allow it to oscillate back and forth, or you just push it in or pull it out and hold it, you've stretched or compressed that spring a certain distance from the equilibrium position. So if you pull it back here, it has a negative X value, and if you pull it out, it has a positive X value. So it's how far from where the end of the spring naturally rests has the end of the spring been pulled or compressed. Okay, so now that we have the force, we can determine what the potential energy is. And we're going to do this once again through work. So we're starting with work non-conservative equals force times displacement. Alright, so we're going to plug in K times X times displacement. And we run into a little bit of issue here. Remember, we can only use this relationship here if the force is constant. But as the spring, end of the spring stretches or compresses, so it's displaced some distance delta D, this X value changes and therefore the force changes. So our force is not a constant value with displacement, so we can't use this method. That's not going to work. So when we have a force that changes with displacement, that means we need to integrate. Alright, so we're going to integrate our spring force equation. And that's going to give us that, let's see, K is a constant. We get X squared over 2. We need to evaluate from X1 to X2. So work non-conservative is going to equal 1/2 K X final squared minus 1/2 K X initial squared. So that means we can define spring potential energy is equal to 1/2 K X squared. Because remember, work is equal to the negative of the change of potential energy. So since this is a final and this is an initial, we have a change in energy here. So we can pull out one of the terms and define what the potential energy is. Sometimes this is referred to also as elastic potential energy because you can apply the concept essentially to anything that's stretchy. I tend to use strings or springs because they are very easy to visualize and they're fairly stretchy. You can pull them out, compress them, rather than trying to introduce a whole bunch of different stretchy materials like a rubber band or like elastic banding. So I tend to stick to springs just to not overly complicate this concept by having different models. Especially since then you have to come up with something other than a spring constant K, you have to have some sort of other elastic constant in there. Now I do want to go out and point something out. I introduced the spring force equation so that we could integrate it in order to find how to calculate work and thus how do you calculate potential energy. And I'm going to add that term into our conservation of energy equation in a second. But I do want to take a moment to stop and point out from the spring force equation If you have an object falling onto a spring, there is a little bit of a habit to try to sum forces at this moment, because you have the force of gravity down, the force of the spring up, and you run into an issue because as the spring is compressing, the force isn't constant. So you end up with this relationship here where you have no idea what this value is here. This should really be a Y. You have no idea what that value is, and it's not a constant value, because as the force changes, what that value is going to change. And really, when you're looking at this, you're not looking at the equilibrium position when it stops, because now there's a force normal rather than a spring force in there. So it's better and less complicated, and one of the reasons why we do this is we've integrated the force function to take into account the fact that the force is not constant with displacement. So by using the energy conservation, we take into account this value is not constant, and our numbers turn out correctly. You don't know what this is, you're never going to be given a problem. And because it is a function and not a constant value. And it's not an equilibrium situation, because once it stops, it's no longer a spring force you're talking about as a force normal. So don't even worry about this. And there's a reason why that spring force equation is not on your constant sheet right now. Now that we learned about spring potential energy, we can add it to our conservation of energy equation. So once again, we have all of our initial energies. So we have one kinetic energy, now two potential energies. And then we have our work non-conservative, so non-conservative forces like friction and air resistance. And then we have our final energy. So once again, one kinetic, two different types of potential energy. And remember, this formula comes out of the work energy theorem. Because remember, the work energy theorem was that work equals a change in kinetic energy. We've just essentially rearranged it, where we have our kinetic energies, and then we have all different types of work. Work due to conservative forces like the spring force and the force due to gravity, and work due to non-conservative forces like friction and air resistance. So this is really just a rewritten form of the work energy theorem, kind of trying to separate things conceptually so you can see that initially we have a certain amount of energy, you may lose some. Every once in a while there are situations where you can gain energy through non-conservative forces, but I don't have the right problems like that. And at the end you have to have a certain amount of energy based upon what this size was. And this constrains how your object behaves in the system, because you can't gain more kinetic energy than you get from the spring that was released to transfer the energy to the object. So that constrains what your velocity is based upon what the spring constant was and how far the spring was compressed that was released that transferred the energy to the object. So the purpose of conservation of energy is to place constraints on our system so we can understand how it's going to behave. So we start with some initial conditions, and based upon those initial conditions, the conditions at some later point in the motion of the object can be determined.